Okay, now we're on to part B of chapter 3, which is on inference. Let me remind you that we've got some data which we're assuming is normally distributed, and we have an estimate which we get for the mean, which is the average of the data values. Now I'm being very careful to write these y's as uppercase random variables because I want to think of this estimate as a random quantity that has a distribution imparted on it by the distribution of the y's. So our distribution for the individual y's is normal, and that imparts a distribution on the estimate. And when we think about it that way, we sometimes call it an estimator. There's more on that vocabulary in the book. I'm not going to dwell on it here. So I want to think about this mu hat as a random quantity. One important feature of any random variable is its mean. So what is the mean of the estimator? Well, we just kind of follow our noses and replace, this is the sum of the yi, so I'm just replacing the definition of y bar, and then by linearity of expectations, there's a good link for that in the book, I can take out any constants and distribute through any sums. I'm just not doing a very good job of writing that out. And then each of our y's has a mean of mu, so this is actually n copies of mu, and then that n is going to cancel. So we get a kind of tidy expression that the expected value of our estimator is equal to the true but unknown quantity. And we also know that this means that this estimator is unbiased because its expectation is equal to the true but unknown value of the parameter. So now we know something about the distribution of our estimate. It's centered around the value that we want to know, that we don't know, which is mu. Okay, how about another cool property, or important, I guess, you might not think it's cool. What about the variance of mu hat? So just again, following your nose, let's write out what these things are. Nothing super exciting so far, but now I can use results about variance. I can bring that constant out front as long as I square it, and I can distribute the variance through the sum as long as we have independence, right? I've got to have independence here in order to distribute the variance through. If the y's were not independent and identically distributed, then there would be an extra covariance term. But since they are independent, that covariance term is 0. And each one of those variances is sigma squared. So I have n copies of sigma squared in that sum. So one of these sets of n cancel, and I get, again, a tidy result. And that result is that the variance of, that's the ugliest mu I may have ever written, is equal to the original variance divided by n. And that's a cool result because it says that as you get more data, you learn something. You may become more confident about your estimate around the true but unknown value mu. The last thing is a theorem that there's more detail on in the book, which says that a sum of independent Gaussians is Gaussian. And what this means is that since we know the mean and the variance of the distribution, the whole thing has a Gaussian distribution with that mean, and a variance that comes from our variance calculation. This is a very important result because we can use it to perform inference. Assuming that sigma squared is known, which is what we did last time, but we're going to do something a little different in a minute. But for right now, assuming sigma squared is known, we can compare this distribution, which is called a sampling distribution, we can compare this sampling distribution to an estimate that we got from data under the null hypothesis, which is that mu takes on, whoops, I messed that up, takes on a particular value. Let me show you what I mean by working with some code. Okay, so I'm going to make a plot, and the x values on that plot are going to be from a grid that I'm calling y grid. And I know what to put for the bounds of this grid because I've done this before, but you can always experiment with this on your own. It's really just making a Gaussian curve that is centered around what our null hypothesis for the mean is, which was 64.5. And then I'm going to plot those as the y values, and then as the x values. The y values are the density of a normal distribution at those inputs with a mean of mu, which is part of our null hypothesis, and a standard deviation of sigma squared, which was 2.5 squared divided by n. And I want this to be a line graph. And I'm missing parentheses. And I've got other mistakes. Oh, that's just because I didn't complete the line. And I know you can't see that because it's blocked by the notes. So this is that plot. This is the Gaussian distribution that comes from the estimate of the mean. Okay, so I made a drawing of that, and then I can overlay my estimate on that graph. And you can see that that estimate is a rare quantity under that distribution. So we can reject the null hypothesis because the estimate is rare under the sampling distribution, under its sampling distribution. A p-value is the integral into the tails of the sampling distribution. I didn't spell distribution right. And we can actually ask R to do that integral. R has an integrate command, and you can tell it to integrate the density of a normal distribution from the mu hat value into the tail, so out to infinity. Just be careful to tell it what the mean of the distribution is and what the standard deviation is, which we get from our calculation. Okay, so the integral into the tail of that distribution is 1.5 times 10 to the minus 5, so it's a really small probability. If we wanted to do a two-tailed calculation, we could multiply that by 2. Got to be careful to do value here so that there's two numbers, there's an error and a calculation, and we don't need the error part. So 2 times 1.5 times 10 to the minus 5 is about 3 times 10 to the minus 5. So still a very small number, a p-value that's less than 0.05. Okay, usually we standardize this sampling distribution. So we take the y-bar value, subtract off the mean, and divide by the standard deviation. And this gets called z. And z values have a normal distribution with a mean of 0 and a variance of 1. So notice how this follows estimate minus the value that you want to know from the null hypothesis, like mu naught, divided by what's called the standard error. So the standard error is this sigma over square root of n. We're going to come across this estimate minus want to know divided by standard error a ton over the next many chapters. Okay, so going back over to R, I can calculate a standardized version. So my standard error is sigma squared over n, but I got to take the square root of that. And then z is mu hat minus mu divided by that standard error. Oops, I better run the lines of code in order. So now I've got my z statistic. This is the z statistic. And then I can calculate my p-value by doing p-norm of z. So if I want to integrate into the right tail, I would do lower tail equals false. So that gives me that 1.56. Then I could multiply that by 2 and get the two-tailed p-value. What's more common is to do 2 times p-norm of minus the absolute value of z. That gives the same number, but the reason for that is your statistic could be in either tail. So if you take the absolute value of it and then put it in the left tail with the minus, then you can use lower tail equals true, which is the default, and in this case gives the same p-value out the back end. So that is the math way of doing what's called a z-test. Now I want to pivot to something a little bit fancier. So let's go back over to, we already are on the notes, so my bad. So it is unsatisfying to assume a particular value of any parameter, but in this case, sigma squared, when we have a good estimate. And by that, I'm thinking about s squared. However, incorporating uncertainty about s squared into our calculation involves understanding its distribution. So I've got to help you unpack that a little bit. Okay, so s squared is a sum of squares. Remember what it is. It's 1 over n minus 1, sum I equals 1 to n of yi minus y bar squared. So it's a sum of squares. So I have to teach you something about the squares of Gaussian random variables. So if yi is Gaussian with a mean of 0 and a variance of 1, then, sort of by definition, the square of that Gaussian random variable has what's called a chi-squared distribution with 1 degree of freedom. And if you have a yi that is not standardized, but you take that yi and subtract off its mean and divide by its variance, then that still has a chi-squared distribution with 1 degree of freedom. So we can use this result already. We know that our estimate has a Gaussian distribution with some mean and variance. So if we take that y bar and subtract off the mean and divide by sigma squared over n, that will have a chi-squared distribution with 1 degree of freedom. Okay, here's another helpful result. If you have a bunch of y's that all have a standard Gaussian distribution, then their sum of squares has a chi-squared distribution with n degrees of freedom. So if you sum up n of them, you end up with a chi-squared n. If instead these y's have a non-standard distribution, then you can just take the mean away and divide by the standard deviation, and you get more or less the same result. So how is that helpful? Well, there's a homework exercise in the chapter. Asks you to show the following identity. So the identity is that the sum of these standardized squares from a Gaussian distribution can be written as the following. This is just algebra. It's nothing fancy. It's just being very patient about the definitions of the quantities involved and manipulating them algebraically. How is this decomposition useful? Well, we just showed that this, pretty much by definition, has a chi-squared distribution with n degrees of freedom. And a little bit before that, we showed that this has a chi-squared distribution with 1 degree of freedom. This is also a sum of squares, and since the degrees of freedom need to add up, this has a chi-squared distribution with n minus 1 degrees of freedom. And that is useful because we can rearrange terms to work out the distribution of sigma squared. So therefore, n minus 1 s squared over sigma squared. I'm really just writing the result again. And so if we rearrange to put sigma squared on the left of the distributed sign, and then minus 1 s squared over chi squared n minus 1 gives us a distribution for the unknown quantity. I really just wanted to draw a good box around that. So there we go. There's our box. Okay, so what does this mean in practical terms? So now we're going to incorporate uncertainty in the variance into our calculations. Okay, first I'm going to do it with virtual data by simulation, and then we're going to do some closed form calculations. So I'm thinking about last time when we did a large number of samples, and I'm going to do okay, so I am going to take sigma 2 samples from this distribution. So I'll do n minus 1 times s squared divided by a random chi-squared random variable with n minus 1 degrees of freedom. Look how I'm following that result. So sigma squared comes from n minus 1 times s squared divided by a chi-squared random variable. And then I'm going to plug that in as the variance of my Gaussian. Okay, so this is a very similar simulation as we did in chapter 2, but instead of taking the known sigma squared value, we're taking a sample from its sampling distribution. And then I can save my statistic which is the mean of those samples. Okay, so let's run all of that. While we're waiting, I will go over to the plot, because in a moment I want to make a plot of these values. And while we're waiting, we can start the visual. Okay, so I'm going to do a histogram of these statistics. Okay, so there's the histogram. Look how that's a discrete version of what we had up a moment ago, which was a nice little curve. But this time, we're taking into account the sampling distribution of the variances. And then if I want to calculate a p-value, well, first I could put the estimate on there. Okay, so it's pretty rare, and I could do the p-value. And multiply it by 2. And get a pretty small number. So 4.8 times 10 to the minus 5. So again, an easy reject of the null hypothesis. All right, let's go back over to the notes. An English statistician working at Guinness Brewing Company in Ireland named Gaussian, publishing under a pseudonym, student, oops, I better spell that correctly, showed that convolving, I'll say what I mean by that in a second, a Gaussian variance over a chi-square distribution, actually it would be an inverse chi-square distribution because it's in the denominator. So what do I mean? I mean that if y is Gaussian with a mean of mu and a variance of sigma squared, but the sigma squareds come from this other thing that divides by chi-squared random variables, that this distribution has a closed form, and it is now known as the student t distribution. I'm not going to show you the form of the student t distribution because it's not important. But we're going to get this thing that's very similar where we take the estimate and divide by the value, subtract off the value we want to know, and then divide by the standard error. But this time, the standard error is using the estimated quantities, S, not sigma. Then this quantity t, its random counterpart, will have a t distribution with n-1 degrees of freedom. So this is still of the form estimate minus want to know divided by standard error, but the standard error is a little different than with the z-test. Under this t-test, the standard error uses the estimated standard deviation of the distribution of the mean. So if I go back over to R, I can calculate a new standard error, which is square root of S squared divided by n, and calculate this t statistic, which is mu hat minus mu divided by SE. Then I can calculate a p-value with the t distribution. So pt minus abst, same trick to make the calculation agnostic to what side of the distribution the statistic is on. And then if you want a two-tailed test, you multiply that by 2. Okay. So there is our exact calculation under the student t distribution, as opposed to the simulation-based one. We get a very similar answer, right? They're the same magnitude, 5 times 10 to the minus 5 or 6 times 10 to the minus 5. Not a very big difference. So this is how you do a t-test.